This integration method is integration by partial fractions, and you could recognize when to use this if you have a ratio of polynomials. And so in that instance, you are most likely going to be using partial fraction integration. Sometimes it could be other things, but that's an option in when you have a ratio of polynomials. And you'll see through the up and coming examples. I encourage you to read this handout because it does describe that a little bit more, maybe give some extra information. But let's just jump right into example problems. And I have all of these pre-done already. I just want to use it in order to demonstrate how to apply it. There's 4 different cases that you will encounter. And the first one is where your denominator is a product of distinct linear factors. And so your denominator, if it doesn't come factored, you may be able to factor it yourself. And if it factors into essentially lines and unique ones, then this is what you're going to do. The denominator here, 2x cubed plus 3x squared minus 2x, factors nicely into x, 2x minus 1, and x plus 2. All 3 of them are lines. The partial fraction decomposition is a over x plus b over 2x minus 1 plus c over x plus 2. And so that is what I have here in this second line. This decomposition has to equal the original fraction, which is what I did. So if you then get it in a common denominator, as I did on the next line, the numerators have to be the same, meaning the a times 2x minus 1 times x plus 2 plus the bx times x plus 2 plus the cx times 2x minus 1, that numerator must be equal to x squared plus 2x minus 1. Since the denominators are the same, the tops must also be equivalent. And so the challenge here is to solve for the unknown coefficients of a, b, and c. And so I set the 2 numerators equal on this line. And then what I do is I notice there's 2 paths to take. The one I'm going to do here is I'm going to substitute values in for x. I tend to choose to substitute values that are going to zero out at least one of the terms. And so in this case, I see that when x is 0, b and c are going to disappear. When x is negative 2, a and b will disappear. And when x is 1/2, a and c are going to disappear. And that's what the table, the next table is showing. So when x is negative 2, on the left side, a disappears, b is going to be multiplied by negative 2 times 0, so that disappears, and c is multiplied by negative 2 and negative 5. So negative 2 times negative 5 is 10 times c equals, and on the right-hand side, when x is negative 2, you get negative 1, which means that c is negative 1/10. The next value I chose was 0. When x is 0, a is going to be multiplied by negative 1 and 2. B disappears because it's multiplied by 0. C is also multiplied by 0. And so we have negative 2a equals negative 1, which means a is positive 1/2. And finally, when x is 1/2, going through the same process, you will get 5/4 b equals 1/4. And when you solve for b, b equals 1/5. So it's at this point that I return to the top blue highlighted section and I plug in the values for a, b, and c. Since that partial fraction decomposition is equivalent to the original function, that is what I want to integrate. And so it's over in this line, where I then integrate the partial fraction decomposition. You could separate the integrals and pull out the constant, so you could have 1/2 times the integral of 1 over x dx, which is 1/2 times the natural log of x, 1/5 times the integral of 1 over 2x minus 1, which will, whether you see it or use substitution to integrate, will come out to be 1/10 times the natural log of 2x minus 1 minus 1/10 of the integral 1 over x plus 2, which is 1/10 natural log of x plus 2. And since this is an indefinite integral, you have your plus c term also in there. And that is the solution to this first problem. Problem 2 is the next case that you might encounter. And over here, this is the instance where you have linear terms on the bottom, but at least one repeats. In this case, you have x minus 1 times x minus 1, which is what the x minus 1 squared is. And so in that case, your decomposition is going to be a little different from what we had just done. In this instance, you're going to have a over x minus 1 squared plus b over x minus 1 plus c over x plus 1. And the numerator has to be a polynomial 1 degree less than what you have on the bottom in its factored form. And so, for example, x plus 1 is a line, c is a constant. X minus 1 is a line, b is a constant. X minus 1, which is the factored form of x minus 1 squared, x minus 1 is a line, and so a is a constant. So don't square it out and expand. Keep it in its factored form and look at what's inside the parentheses. And that's how you could tell what type of numerator you should have. You'll see in subsequent problems that a constant isn't always what you need on top. So going through the same process, we get a common denominator, and then you set the numerator equal to 4x, which was the numerator of the original function that we were integrating. And so this is now the equation I'm using in order to solve for a, b, and c. For this one, what I did was I factored based on the x terms. So the coefficients of x squared are b plus c. The coefficient of x is an a minus 2c, and the coefficient of 1 on the left side is a minus b plus c. On the right side, there is no x squared. You could view x squared as a 0 times x squared, which is why b plus c is set to 0. Likewise, there's no constant term, so you could view 1 as secretly multiplied by 0, which is why this equation is multiplied by 0. But there is an x term whose coefficient is 4. So the coefficient of the x term on the left side, which was a minus 2c, must equal 4. So 3 equations, 3 unknowns. You could use a variety of techniques in order to solve for them, but what you should discover is that a is going to be 2, b is going to be 1, and c will be negative 1. So go back to the decomposition, which I have in the top left, and plug those values in their appropriate places. And then what's left is to integrate. The first integral can be solved using u substitution, and you will get the integral of 2 over x minus 1 squared is negative 2 over x minus 1. The integral of 1 over x minus 1 is the natural log of x minus 1, and the integral of 1 over x plus 1 is the natural log of x plus 1. And so the final solution I have over here with the plus c, and using log rules, you could combine the log of x minus 1 minus log of x plus 1. A log minus log is log divided by the other log term, which is where the log of x minus 1 divided by x plus 1 came from. It's not necessarily required to put it in that form, but it's a little simplified. Continuing on to the third case, here the denominator factors into t times t squared plus 4, so it's not all linear. T is a line, t squared plus 4 is a quadratic function, and so when you do the decomposition, t being a line has a constant a above it. T squared plus 4 being quadratic needs a line on top of it, and that's where bt plus c comes from. Now, again, get a common denominator, set the numerators equal to each other, which is this line here, and then use either of the two techniques I demonstrated in order to solve for a, b, and c. In this case, I did what I did in the second case, which was I noticed that a plus b are coefficients of t squared, and the coefficient of t squared on the right is 2. So that's my first equation. I noticed that the coefficient of t on the left is just going to be c, and negative 1 is the coefficient on the right, so they are equal. And the coefficient of a constant is 4a on the left and 4 on the right. And so we have that a is 1, c is negative 1, and b is going to be 2 minus a, which comes out to be 1. Plug those in and integrate, and it requires a little bit of work, but the integral of 1 over t is the natural log of t. Dividing the t minus 1 by t squared plus 4, you could get two new integrals, which I have on the right here. And the first integral is going to be solved by u substitution. The second integral is essentially an arctan, and you need to figure out arctan of what. And so this first integral I did next using u substitution with u equal to t squared plus 4. And I solved, and I got 1/2 the natural log of u, which is 1/2 the natural log of t squared plus 4. The last integral of 1 over 4 plus t to t squared, I brought a 1/4 out, which gives me a new denominator of 1 over 1 plus t over 2 squared. That you could solve using u substitution now, where u is t over 2. This is going to give an integral of 1 over 1 plus u squared. There is a 2 there now, but you can bring the 2 out. And this is just an integral that is arctan of u. And u being t over 2 becomes arctan of t over 2. The 1/4 and the 2 that's inside the integral simplify a little bit, and that's where the 1/2 coefficient comes from. When you combine all of these integral answers, you get the natural log of t plus 1/2 natural log of t squared plus 4 minus 1/2 arctan of t over 2 plus c. And that would be your answer for this third problem. Fourth problem, I start you off on. I'm not going to solve it, but I will give you what the answer is. And in this case, this is where you have repeated quadratic factors. So we've built up in complexity. First, we had distinct linear terms. Then we had some repeated linear terms. Then we had distinct with a quadratic term. And now we have a repeated quadratic term. And so here, your decomposition is going to be a over x minus 1. A is constant because x minus 1 is a line. And then all the other terms are linear on top and quadratic on bottom. Notice that you always go from the factored form and its power, and you keep decreasing the power until it's 1. So the factored form of x squared plus 1 cubed is one denominator, then it's x squared plus 1 squared, then x squared plus 1. Again, don't envision the expanded form. View the shape from the factored in parentheses form. And since they're all quadratic, you have a line on top. So here there are 2, 4, 6, 7, 7 unknowns, 7 coefficients to solve for. Another hint, by the way, in all of these problems, to know how many coefficients you'll need in your decomposition is to expand the denominator, or at least envision the denominator, and take note of the highest power. So x squared is going to be cubed, which will give you x to the sixth. Multiply that by the x minus 1, or the x part of it, and you get x to the seventh is going to be the highest power, highest term, which means 7 coefficients are needed. So your answer, your decomposition, should have 7 letters, which we do. I'm going to leave it to you to actually work through this. It is going to take quite a bit of work, but I will give you the answer so that you can check yourself. And this is in its most simplified form. But the answer will be 3/8 times the natural log of x minus 1 over the square root of x squared plus 1 minus 1/16 arctan of x minus 1/16 of x cubed minus 6x squared plus 3x minus 4 divided by x squared plus 1 squared. And then plus c for the indefinite integral. So it's good practice. I know it's the hardest one, but it has everything you need in it from the 3 previous problems. Take your time, be creative with how you solve all of the integrals, do one integral at a time, because some are solved directly, some may require you substitution or some other kind of trick. But this will be your final answer. Good luck, and that is it for integration methods.